Welcome to lecture 5.2, where we're going to be looking at definite integrals. In the last section, we saw that we could compute the area underneath a curve by using rectangles, and that if we divided an interval into an infinite number of rectangles, or set the number of rectangles going to infinity, the limit as n goes to infinity, that if we calculated the area of each of those rectangles and added it together, that we would then be able to compute an area under a curve. In general, when we start with a function, we divide the interval between a and b typically into an equal number of partitions with the same width, but that doesn't have to be the case. We don't have to make each partition, like here in this for A1 could be wider than A2, could be wider than A3, but typically we divide the partition into equal partition amounts, interval lengths if you will, and so far in the last section we looked at selecting left-hand values for the height of the rectangle, or selecting right-hand values. And what this curve is suggesting is that you don't really have to pick any specific value as long as you pick a value inside the interval or inside the partition. So you can see here x sub 1 is actually not in the middle or on the left or the right. X sub 2 is the same. The only one that looks like it's any kind of value is like maybe x sub 4 looks like it's the center or the midpoint of the partition A4. So again, the area is calculated by dividing it into partitions, dividing the interval from A to V into sections, and then picking a test point in there, a point value for the height of the rectangle. Okay. We then choose sample points in the subintervals. We typically, in the last section, we picked left endpoints or right endpoints, but really any number between the endpoints is allowed. Okay. This is actually called a Riemann sum. Pardon me. And then we calculate the area of each triangle, the width of the area, the width of the rectangle, excuse me, I said triangle, I meant rectangle. The width of the rectangle is the delta x, so delta x sub 1 is this width here. And then f of x sub 1, this is our test point in partition 1. Notice we go up to the height of the function and then we draw a bar across there. So this value we can know by plugging in x sub 1 into f of x. And then we have to do that in each partition. It's just a little bit easier if we make the partitions equal width apart, so each one has the same width for the rectangle calculation, area calculation, and then if we pick consistent points to sample points to find the height of the rectangle or the length. So here we have a function that's actually going below the x-axis. So notice in this diagram both A3 and A4 are negative areas, if you will. Now we don't typically think of area as negative, we think of it as an absolute value. But imagine this function was, let's say for example, a profit function. And the area under the curve is going to give us the accumulated profit over the period from A to B. Well, notice that A3 and A4 represent a negative profit or a loss. So really we want the overall profit for this period would actually be subtracting out these negative values. So notice here in the notation that if we did the sum, the Riemann sum of this graph, we would have A1 plus A2, which are both positive, minus A3, which is negative, minus A4, which is negative, and plus A5, which again turns positive. And this would give us the net area, the net value of the function under that curve. So the definition of a definite integral, if a function is defined on an interval AB, the definite integral of f from a to b is the number, the integral from a to b of f of x dx equals the limit as the delta x goes to 0 of the sum of all the rectangles from I to n, how many rectangles you have, of f x sub I, of all the height of each sample point times delta x sub I. Now this, this is a general form, and notice that our limit now changed from n goes to infinity to delta x goes to 0. Okay, it's a little bit clearer, I think, with n going to infinity, meaning that we have an infinite number of rectangles. Here it's saying the same thing. It's just saying the width of each rectangle is 0, so each rectangle is becoming basically a line, and it's the same thing. Note that if you're on a test and it says to find an integral, a definite integral, using the definition, then you need to use the Riemann sum, not the shortcuts or the rules for finding integrals. Okay, so if you're asked to find an integral using the definition, you need to use the Riemann sum. You need to do the calculation of the rectangles. Okay. This is also an interesting side theorem. If the function is continuous, but it does have, if it's continuous, we know it's integratable all the way through. But some functions have a limited number, a finite number of jump discontinuities. It's still possible to have these jump discontinuities and the function to be integratable over that same interval. And so it does still exist. This is an interesting, weird situation in calculus. Okay. So if it is integratable, then we know that delta x is going to be the interval, the difference between the interval b minus a over n, which is the number of rectangles. And each x value is going to equal wherever you start, wherever you start, a plus I times delta x. All right. This is important when we're trying to solve these Riemann sums, which we're going to look at. Okay. The nice part here is that the Riemann sums, because the y value is going to be negative below the x-axis, is automatically going to subtract out these negative values. And interestingly enough, when we're just solving for the integral, that works as well. Okay, that works as well. All right. So this first thing is just asking us to rewrite this as an integral in the interval from 0 to pi. Okay, so this is asking us to take the right side of the equation here, written as a Riemann sum, and rewriting it as an integral. Okay, so notice here where the integral is going from 0 to pi, so this is our limits on our integral sign. Our function are the, what is the function of x? And so our function is x cubed plus x sine x. And then instead of delta x, we have dx. So this is just a simple exercise in making sure you recognize how to move from a Riemann sum notation to an integral notation. So this is really just a notation kind of exercise. All right? These are really important when we're trying to figure out how to solve Riemann sums. And remember, if you are asked on the test to find the integral, the definite integral, using the definition, you have to use a Riemann sum to do that, because that's the definition, not your shortcuts. These three formulas on the left are very important, and you need to memorize these. That if I isolate a summation of I, that I can rewrite this in terms of the number of rectangles as n times n plus 1 over 2. Excuse me. If I have the summation of I squared, this can be written in terms of n as n times n plus 1 times 2n plus 1 over 6. I cubed is n times n plus 1 all over 2, and that whole entire quantity squared. You need to memorize these three formulas. These are more rules, that the summation of a constant is equal to n times that constant, and you would have this anyway as if you took the integral. And then the rest of these other three are similar rules that we have for derivatives and integrals, that if we have a constant times a function We can pull the constant outside. We do this for integrals and derivatives. And if we have the summation of a sum or the summation of a difference, we can do the summation of each part. Now this is very important when we're going to start trying to rewrite it in terms of these formulas on the left. So let's see how that works. Okay. Now this A part, I'm not really, you can see the whole answer there. This is pretty straightforward. So the answer to A is here highlighted in green. So remember, I'm going to look for a delta x. I'm going to figure out how wide each interval is, the width of each rectangle. Notice that I want to take right endpoints. I'm going to start at 0. I'm going to go to 3, x equals 0 to x equals 3, and I want 6 rectangles. So my delta x, again, is this formula b minus a over n, or 3 minus 0 over 6, and gives me 1/2. So each rectangle is going to be 1/2 unit wide. Now it tells us to take right endpoints, so I'm going to have 6 right endpoints because I have 6 rectangles. I'm starting at 0, but I want the right side of the rectangle, the right endpoint. So the height of the first rectangle is going to be 0 plus delta x, which is 1/2. So my first rectangle's height is going to be f of 0.5. The height of that rectangle times the delta x 1/2. The next one is going to be a half away, another plus delta x 1/2, so f of 1, then f of 1.5, f of 2, 2.5, and f of 3.0. Since delta x is in all of these, I can use the distributive property and pull that out, and then just sum together all of the heights of the rectangles. And you can see in here that 1, 2, 3, 4 of the rectangles are negative, and 2 are positive. These rectangles are above the x-axis, these first 4 are below, and then I do a simple summation. So my estimate here for these 6 right edge rectangles is negative 3.93. Okay? It's also asking us in part B to evaluate the same function as an integral, but here you're going to use a Riemann sum as well, not a shortcut. A Riemann sum, not a shortcut. All right? So here we need to rewrite the formula for the Riemann sum. Since remember that when we're doing the actual definition, the n is going to go to infinity. So when we write the delta x, we're going to do b minus a and keep the n. We're going to have an interval. Our interval is from 0 to 3. So 3 minus 0 is 3. And we're going to keep the n because this is part of our formula. All right? By definition, when we have an integral, a definite integral, this is the limit as n goes to infinity from the summation from I equals 1 to n of f of x sub I times delta x. Well, we got the delta x here, 3 over n. And now we have to figure out what x is. Now remember, the value of x is simply our starting point plus 3, the delta x times I. So it's our starting point, in this case 0. So this is finding our first value of x. 0 plus 3 over n would give us our first delta x, and then plugging an I in there will give us each one in order from I to n, from I equals 1 to n. This is a really important step, and because some of this is not very intuitive and you have to think it through, notice what we're going to do is if this function is our f of x, we're going to need to rewrite this function x cubed minus 6x, replacing x with 3i over n. And that's our next step. So I find this first step, although it's kind of maybe not so necessary, it helps me to see what my x is and what my delta x is, and then I want to rewrite this whole thing. Okay, I want to rewrite f of x in terms of f of x sub I. All right. So I'm going to have x cubed will become 3i over n, because that's my x in this problem, cubed, minus 6 times 3i over n. Okay? My x cubed, since my x is now 3i over n, it's 3i over n cubed, minus 6 times my x, 3i over n. Now you'll notice that the 3 over n came out in front. Well, this is like the last example. Remember that since we're using the same width for all of the rectangles, we can pull this out by distributive property and then add up all of the heights of the rectangles. All right? Now, this is very important when you're evaluating integrals using the definition. What we're going to try to do here is isolate the I. So we want to get this I alone and this I alone and everything else outside. All right? So we're going to apply those principles of summation, and as soon as we isolate the I, we know we have formulas for I squared, and I cubed in terms of n that we can rewrite them. All right? It's very important that you notice that this is the limit as n goes to infinity. If you're showing work, you need to show the limit all the way through. So now let's just expand this. 3i cubed is 27i cubed over n cubed, and we compute this. And negative 6 times 3i over n gives me negative 18i over n. Okay? So since we're actually moving towards isolating the I, notice we've pulled the I out of the fraction and just put it in front. And that helps us to see it a little bit better. Okay? Now, since I'm taking the summation of a difference, I can take the summation of each part. That's one of our rules. Just like a derivative, if I'm taking the derivative of something minus something, I can take the derivative of each part and subtract them. So I'm just going to write this separately. And notice what I've also done here is I've pulled the 27 over n cubed out in front. 27 times 3 is 81. N cubed times n is n to the 4th times the summation of I cubed. Hey, that's great. Now I can rewrite this piece as that formula we have. We'll look at that in a minute. I do the same thing minus another summation, a Riemann sum here. I pull the 18 out in front. 18 times 3 is 54, and n times n in the denominator gives me n squared. So I've just separated this into two Riemann sums, and I've pulled the multipliers or the coefficients outside. All right? So now I'm going to rewrite this using the formulas that you need to memorize. I cubed is n times n plus 1 squared over 2, and I is n times n plus 1 over 2. So let's rewrite that. Okay? So all I've done now is use this substitution, and I've substituted in here the summation of I cubed. I've got the formula. The summation of I, I've got the formula. All right? Now, notice if I square the denominator here, I get 4. I want to move that outside of this n factor, and I want to move the n fourth inside so I can do some cancellation. It's a little bit confusing, but notice since it's n4 outside, if I wanted n to the power of 4 and I moved it inside of a square, inside it would become n squared. Sorry I don't have this written for you to visualize. So this 2 comes outside and is a 4, so I have 81 fourths. And then in here I have n times n plus 1 over n times n. Well, immediately you can see that one of those n's would cancel, n over n. And then I have n plus 1 over n left. If I divide this into two fractions, I get n over n plus 1 over n, just separating it with the same denominator. Well, then I get 1 plus 1 over n, and we'll see that in a minute. Here I'm just going to switch sides, so I'm going to move the 2 over here, so 54 over 2. 54 divided by 2 is 27, and again I'm going to have the n times n as the denominator on this side of the product. Again, one of the n's will cancel out, the outside multiplier, so I have n plus 1 over n again. If I make that into two fractions, notice I get n over n, which is 1, plus 1 over n. And that's what you see here. N plus 1 over n simplifies into 1 plus 1 over n. Why do we do this? Because remember that if n is going to infinity, and the only variable n that I have is in the denominator, 1 over infinity goes to 0. So this term goes away, this term goes away, and I can solve this. So I have 81 fourths times 1 squared, which is just 81 fourths, minus 27 times 1. And so I get my answer is negative 6.75. Again, the important thing here, the steps here are, when you're asked to solve a definite integral using a Riemann sum or the definition, first find your delta x. Define it in terms of n. So you should have a number over n. b minus a over n. Remember, then you need to find your x value, so you can substitute in your f of x for f of x sub I. And this is simply the first, where your a value is, a plus delta x sub I. In this case, since a was 0, we just have delta x sub I, or delta x 3 over n times I. Once we have that, we do the substitution. We had x cubed, so it's 3i over n cubed minus 6, 3i over n. These are our x substitutions, f of x sub I. And then we keep working through the algebra until we isolate the i's, and then substitute in these formulas that you need to commit to memory. Let's look at another problem. Again here, we're asking you to evaluate this using a Riemann sum. So the first thing we have to do is figure out what the delta x is. Remember, delta x is b minus a over n. Here I have 5 minus 2 over n. 5 minus 2 is 3 over n. So in this case, we actually have the same delta x. All right. Now our our x value, though, is going to be different. Okay. In general, we have f of x sub I delta x, which is f of 3i over n. It's just the delta x sub I. But in this case, we're not starting at 0, we're starting at 2. So we need to change this x value to be 2 plus 3i over n, because again, we're starting at 2, so we need to go from 0 to 2 plus 3i over n to find our first x value. Okay, did you see that? So again, although our x is typically in this formula, x sub I is simply delta x times I, since we're starting at the lower limit of 2, we have to add that in to our x value. This is really important, okay? We need to have this x value so that we can rewrite f of x into f of 2 plus 3i over n. X is now equal to 2 plus 3i over n, which means everywhere we have an x in this formula, we're going to substitute 2 plus 3i over n. All right? So notice here we get the limit. This is normal, 3 over n. We've pulled the width of the rectangle out since it's constant across all of them. It's the same across all of them. From I equals 1 to n. 4 is just a constant, so we're fine there. Minus 2, this is the 2x, but x is no longer x is 2 plus 3i over n. So we put that in parentheses. Now let's do our algebra and clean that up. We get 4 minus 4 minus 6i over n, which notice gives us simply 4 minus 4 is 0, so we get negative 18 over n squared. Why is it n squared? Notice what we've done is we pulled the 3 inside, we've pulled the n inside, and so we've multiplied across. We get negative 18i over n squared. So we've just taken this 3 over n, multiplied times this negative 6i over n. Again, we've got our I isolated, so we can use our formula that we need to memorize to do the substitution. So I get the limit as n goes to infinity of negative 18 over n squared times n plus 1 over 2. Again, this is simply a substitution of the formula for the summation of I. All right? I'm going to do the same thing. I'm going to pull the 2 over to the left. I'm going to put the n squared inside of that parenthesis. One of those n's is going to cancel. Then I'm going to have n plus 1 over the n that's left. N over n is 1 plus 1 over n. Right? I see this, and again, remember that as soon as I have this, my only n is now in the denominator. As n goes to infinity, this goes to 0, this one term, 1 over n, and so I'm just left with negative 9. Okay? Definitely practice some of these. These are probably the most challenging problems on Chapter 5 test. When you see a problem here that says evaluate the following integrals by interpreting each in terms of areas, what this is saying is that you should recognize the geometric shape. So you want to look at the graph and see what's going on. If we look at the graph for A, hopefully you notice that this is 1/4 of a circle. Okay? And it's a circle with a radius of 1. We could rewrite this equation as x squared plus y squared equals 1, which is the equation of a circle with radius 1. Hopefully you know that the area of a circle is pi r squared. Pi r squared is the area of a circle. And since we're only looking for 1/4 of that circle, 1/4 of that, we're going to have pi times r, which is 1 squared, or just pi, divided by 4. Okay? We want 1/4 of the circle, pi r squared, and so we get pi over 4 for the area. So here we didn't actually, here we use some kind of common sense approach or a geometric approach to finding the area under a curve. Here I see that I have a linear equation, so this is a straight line from 0 to 3. If I graph this line, I can see I actually have two areas, one area above the curve and one area below the curve. Below the x-axis. So I can calculate the area of the triangle A1 and subtract the area of triangle A2. Well, the area of a triangle is 1/2 base times height, and each of these are pretty easy. This A1 has a base of 2 and a height of 2, so I have 1/2 times 2 times 2, or 1/2 of 4, which is 2. My A2 is a triangle with base and height of being 1, so this is 1/2 of 1 times 1. And remember, I'm subtracting this A2 triangle because it's negative, and when I do that, I get 1.5. So when it's asking you to kind of evaluate an integral in terms of its area, it's asking you to look at what is the geometric shape, and then just use your basic geometry knowledge of areas. The midpoint rule is really this more of a concept, and this is saying in the past chapter we did left endpoints, we did right endpoints, and we saw in the very first examples we did that I think the right endpoint was an overestimate, the left endpoint was an underestimate, and that's not always true. It really depends upon the shape of the curve. But if your idea is to get as close an approximation as possible, in general, it is usually better to choose x sub I to be the midpoint of each rectangle. And this kind of makes sense because if they're always right and the curve is up, then you're going to have over and or under, etc. So if you pick the middle point, in general, you're going to have better estimates. And so all we have to do is to look at each interval and divide by 2 to find the midpoint. Okay? So here's an example to kind of approximate to find the integral with 5 rectangles using the midpoints, and we're going from 1 to 2. So notice the distance apart in this interval is only 1. So each rectangle is going to be 0.2 units apart, or 1/5 of a unit apart. Okay? So the endpoints of the intervals are, since we're starting at 1, the right side, so we have a left side and a right side of the first rectangle. It goes from 1 to 1.2, and then 1.2 to 1.4, 1.4 to 1.6, etc. So the midpoints in each rectangle, here's the first rectangle, it's from 1 to 1.2, is the value at 1.1. The midpoint between 1 and 1.2 is 1.1. So although we're going to find the height at 1.1 by plugging that into our original functional value, and then the height of the next midpoint, the height of the next midpoint, the height of the next, etc. This is very easy to do in our calculator. We can do this all at once. Your calculator will actually do order of operations. So you could put 0.2 times, actually no, you would have to use parentheses here because we're multiplying times this whole sum, my bad. 1 divided by 1.5 plus 1 divided by 1.3 plus 1 divided by 1.5 plus 1 divided by 1.7 plus 1 divided by 1.9, close parenthesis, and then times 1 divided by 5, or 0.2, and you get this answer. So this is just another example, in this case asking you to find the value here using midpoints. This is an approximation, and you can see the squiggly equal sign, which means approximate. We've already looked at some of these definite integral properties, just reminding you again that if we're taking the integral of a constant, it's going to be that constant times the difference in the interval. If we have a sum, we can take the integral of each part. If we have a coefficient, we can pull the coefficient out. And if we have a difference, we can take the integral of each part. I'm not going to spend any time on these. These are getting very familiar two other ones that are kind of more important, or just interesting concepts. If we take the integral and we have the same limit, this is saying find the integral of the area under a point. Well, a point doesn't have any measurement, so to speak. A point is kind of a concept. It's not a mass, and so there is no area under a point, and so this will always equal 0. This other point is saying if we change the limits from b to a to a to b, that these values will be the same numerically but opposite sign. Okay, so this is another interesting phenomena. Okay. One final thing is that if a, b, and c are in an interval and c is between a and b, then the integral from a to c plus the integral from c to b is going to equal the integral from a to b. Okay. And you can see that these are connected, so we have to have these 3 points connected, and this end point here be the beginning point of the second one. All right, and you can see this better visually in this graph. So that, which makes sense. The integral from a to c is going to give us this area. The integral from c to b is going to give us this area, and so combined it would give us the total area. So this is just a concept problem looking at this, and so we know that the area from 0 to 10 is 17. And a sub-area from 0 to 8 is 12, and it's asking you to find the area from 8 to 10. So it's kind of like from 0 to 10 it's 17, from 0 to 8 it's 12, so this other area would have to be what? 12 plus what gives me 17. And you could even put these in order. From 0 to 8 plus 8 to 10 gives me the area from 0 to 10, so I can look at each piece. Well, here it solved it. And I get 17 minus 12 equals 5. This is pretty straightforward. Again, I'm not going to spend a lot of time there, but you can look at that again and try